So, good evening to all. On behalf of Kerala Science Forum, I extend you all greetings to you all and welcome to you all. This is the 70th lecture of Popular Science Lecture Series. It was started in 2018. So, till 2018, we were conducting the meetings in the ground floor. We used to have 300 people attending the meeting. In 2020, the last meeting was held in February 18 at the same hall. So the last meeting was on the topic of the coronavirus. Someone who did the research on coronavirus in Arizona University, she came back from there doing research for 7 years, and she was doing some research on the spike protein, and she was announcing that when this SARS-CoV-19 virus was identified, she was explaining what is that. It was our last lecture. Then we went into the online mode. The online mode it was years of 18 to 45 we held it on online mode. Then 45 we returned back to the house. Still we have a problem of bringing back the whole audience to the hall. The numbers are less. Anyhow, if you look at we are placing all our the lectures in the YouTube channel, PSL YouTube channel. If you go and look at the YouTube channel, everything has a hit of around 300 to 400. Again, attendance is maintaining, but people are seeing it in the literally manner and they are seeing it from home. Some people are watching from home as well. Anyhow, it is reaching a large audience. Let us have the meeting. So let me introduce the Tamil Nadu Science Forum. Tamil Nadu Science Forum is a voluntary organization. It was started in 1980 by few researchers in Madras University. One of the researchers, Dr. Morgan, is sitting here. Along with Dr. Morgan, Dr. TRB was the last one of this PSL. He is not available today. He is working for, he is doing some work in the Kriya University and he is busy with his academic activities. So he is not there, but from 1980 onwards, the Science Forum was conducting a lot of meetings and hall meetings. In 86, we decided to go to the people instead of making them attend the meeting in the hall. It was their turn. So what we did is we started developing some modules and go to the streets and go to the places, the people's places, and do lectures, demonstrations, so many things are there. And we also conducted a jata. It started from Kanyakumari and reached Chennai, and we went to various places and propagate the science. Thereby it expanded throughout the Tamil Nadu. Now TNSF is expanded into Tamil Nadu. In all districts we have the district units. We have membership covering more than 30,000 memberships. And Tamil Nadu Science Forum is running a couple of magazines, one in English, another one in Tamil. In English is Jantar Mantar, it is meant for students above +2 level. And Tuli is Tamil, it is below +2 level students in Tamil. There are 2 magazines. We are publishing science program as science publications as well. A lot of books have been published, popular science books by Tamil Nadu Science Forum. And we are also working on the gender equality. So we want to bring more women in science. That we have a separate organization called SAMAM, which talk about bringing women in science. We also have Youth for Science. There are multiple activities. I want to make an appeal to this science that become a member of Science Forum, and you can choose your area of interest. You can work on. We are working on health. We are working on education. We are working on environment. So many things are there. We are working on apart from popularizing the science. I am doing the activity of popularizing the science and little bit involved in the development and the environment. Because I am an engineer, I am working on environmental activities. So I want to learn those things. So you have space for working on that. So today's lecture is going to be delivered by Dr. Rajnish Kumar. Let me have a short introduction about him. So many of you might have read news about him in November 23 in Hindu. So that's why, I came to know about that. He was doing a research in the carbon capturing, and he won the Shanti Swarup Bhatnagar Prize, which is the highest prestigious award given by Government of India for any scientist. He got an award. Immediately I started looking for him. It's a problem for all. No, we have a person who's standing before us who won the prestigious national award for science. So he is a professor, and he is a first year is a professor in the Department of Chemical Engineering, IIT Madras. Prior to this, he has served as a senior scientist in CSIR National Chemical Authority in Pune, NASI, and the research associate at the National Research Council of Canada. He is his PhD from the University of British Columbia, Canada, and he has research interest in gas hydrates, carbon dioxide capture, process development, and scale-up. Work from his research, more than 100 research articles. He was recognized as a highly cited researcher in the year 2018. Rajnish is the most recent awardee of the Shanti Swarup Bhatnagar Prize for his contribution to the engineering science. Rajnish is also a recipient of NASI Scopus Young Scientist Award for chemistry in the year 2016. More recently, in 2020, Rajnish received the YBG Verma Award for excellence in chemical engineering teaching in IIT Madras. Rajnish sits in the editorial board of many journals, including the NASI, Arts Engineering, AU, and Scientific Report. So, welcome you, sir.
So, let me thank the organizer and for inviting me here. So, since we are already running late, I'll try to move on. The topic which you have seen resembles very much what's written over here. I have just added few words here. So, what we are going to look into why and how of carbon dioxide capture and storage. I don't like to use the word storage, but it was suggested that I use the word storage, which is much easier. I typically use the word sequestration. So rather than storage, I suggest that one should use the word sequestration. We'll talk about it. And then how sustainable this approach is what I'm going to basically give you a brief idea about what exactly is carbon dioxide capture, utilization, and storage, and how sustainable is this particular process. So this is already, but then let me tell you that whatever questions you have or any other reason you wanted to contact me, you can always drop me an email at rajnish@iitm.ac.in. With that brief introduction, let me tell you why exactly we have gathered here to discuss about CO2 capture. So if you look into this particular plot, unfortunately it's not very much visible here, but this is little data and deliberately I have put it over here. So this is the data of 2018. Okay, and if you look into this particular data, it was predicted that we are going to have an imminent peak of CO2 emission by 2020. And if I have to remain below 2 degrees rise compared to pre-industrial revolution, it is going to go like this. For example, by 2100, I could become net zero and it would be fine. So we would be able to basically achieve the target of 2 degrees rise of global temperature if we basically decarbonize our systems at this rate, so that by 2100 we are net zero. So that was supposed to be 2 degrees. But if you have to remain below 2 degrees, then the rate at which you have to decarbonize is going to be much faster, and then you'll have to achieve that by 2080. And if you have to remain below 1.5 degrees, you have to achieve net zero by 2050, roughly 2052. Now, unfortunately, what has happened after that, there was a COVID, and then we have again gone back to our usual stuff. So that imminent peak has obviously has not even happened today. Looks like that imminent peak is going to happen by 2030. So last year, the total global emission of carbon dioxide was 41 billion tons. Okay, 41 billion tons. That's the global emission. So if you talk about these numbers, we are talking over here. Every peak. So if I have to become net zero, then I have to start working on decarbonizing our industries, decarbonizing our pretty much everything. We'll have to talk about that in this particular presentation. If you look at from this particular slide, I have given two different scenarios. Again, data comes from this source over here. To have a 50% chance of keeping warming below 1.5 degrees, the world can only emit 250 billion tons of CO2. So depending upon what is the concentration of CO2 in the atmosphere today, if you have to basically predict like when we would be able to achieve a particular temperature, at what concentration of CO2 in the atmosphere I am going to achieve that. So with that calculation, it turns out that we have a credit of roughly 250 billion tons. If I emit 250 billion tons, the CO2 concentration in the atmosphere is going to be a number where the global temperature will rise around 1.5 degrees above the global temperature which was present during the pre-industrial revolution. This is the target pretty much, that you have to reach that temperature. Okay. So if you talk about 250 billion tons of credit, today if we are producing 41 billion tons of CO2 every year, it basically means that by 2030, we are going to basically reach that 1.5 degree target. So it was predicted just 5 years back that we would reach that by 2050, and within 5 years, we have emitted so much of CO2 that we are now talking about 2030. Now the question is that 2030, obviously we cannot reach this target. So we have already missed the birth of 1.5 degrees. Whatever people talk about that we would ultimately go to 1.5 degrees rise of temperature compared to pre-industrial time. Now if we assume that this is not possible, let's move into this plot over here. In this particular plot, the data basically says keeping global average temperature right below 2 degrees centigrade. Okay, now if you have to keep it below 2 degrees centigrade, for a 50% chance of global average temperature going below almost around 2 degrees of the pre-industrial time, you have a credit of 1150 billion tons of CO2. That basically means if I am going to emit at the same rate as around 41 billion tons of CO2 every year, I am going to hit this target of 2 degrees by 2050. Okay. So it basically means that if I am not going to decarbonize ourselves, that by 2050 at the same rate, it is increasing, by the way. The global CO2 emission rate right now increases by roughly 1 to 1.5%. Okay, so it is increasing. But let's say if it stops increasing from today onwards, and if we keep emitting 41 or below that, it basically means that by 2050 we will have a chance of basically reaching around 2 degrees above the pre-industrial level. And this is kind of going to be too much. So very frank, it's not going to be that easy. We are already seeing that kind of challenge. So if you have to do this, if we have to cut down the CO2 emissions, what exactly has to be done? Okay, and if you look into this particular slide over here, a lot of information, I'll come back to this slide at some point of time, but if you look into this orange ones over here, it basically talks about energy efficiency. So what typically it means, since we are, as a scientist, we don't really understand how we are going to decarbonize, so we try to basically put the blame on efficiency, and we put the blame on you, that you pretty much try to save the electricity or whatever you are trying to do, so that we achieve our target. So in this case, industry has to improve most of the CO2, cut most of the CO2 emissions by improving energy efficiency. Same is the case with transportation, same is the case with buildings and other cases. Okay. Only in power there is not much of energy efficiency. I'll talk about it maybe later if I have some time. But let me give you just one single example. I'll tell you, I don't know how many of you are aware of this fact. See, in 2080s, in 1980s and 90s, we used to run a car called Maruti 800 or something like that. You know what was the mileage of that car? Typically 10, 12 is what we will get. Today, with all the development in efficiency of engine and all, and still in the city, your mileage not goes beyond 10. Sometimes it is below 10. So I'm trying to tell you, just please keep this in mind. Increasing efficiency is not going to be very easy. Now, what we have done though, see, in those days, if you had to go to Bangalore probably because of bad road conditions or not sufficiently good quality roads, you might take 10 hours to reach there. Okay, today, since the roads are better, not the Bangalore road though, some other roads, let's talk about that. So if you really can travel the same distance in half the time. So what actually has improved is that it's not the efficiency, it has improved the overall CO2 emission has come down because we are reaching there at a much shorter period of time. So we have to, what I'm trying to point out over here is that efficiency will certainly, I don't know how much efficiency increase we are going to achieve, but we have to basically find other ways to cut down our CO2 emissions, and this is what we are going to basically talk about. Now, so in this particular case, if you look into the other, in the power sector, it's the renewable which people talk about. That the total emission in the power sector is maximum. The CO2 emission we talk about in the power sector, roughly 67% of our total CO2 emission comes from power sector. The reason is, I'm sure all of you know, that mostly we depend on coal for electricity production. So the CO2 emission from power sector is maximum. And the remaining is from industry. When you talk about industry, the two prime industries are steel industry and cement industry. They pretty much share the roughly 8%, roughly 16 to 17% of total CO2 emission comes from alone CO2 in the cement industry and steel industry. Remaining transportation and all are there. So, but if you look into this, in two of these cases, in the case of power generation, it's talked about that we are going to move from coal to renewable. And in recent past, you have seen there has been a lot of effort. I'll talk about it in the next slide probably. But then, one important point over here is that we have to focus on two things in this particular slide. I have already kind of glossed through this efficiency part, but what we have to focus on, identifying renewable source of energy, which is going to reduce the CO2 emission significantly if we can do that. And the second best solution is to by doing carbon dioxide capture, utilization and sequestration, which is denoted here by this blue one. Okay, so we are going to basically reduce total 700 billion tons of CO2 by 2050, either by moving from non-renewable to renewable, or by doing capture and utilization and sequestration of carbon dioxide, and also by improving the energy. And then there are other fuel switching. Fuel switching basically mean that those fuels which does not come under the category of renewable or non-renewable, like nuclear fuel, will basically come under this particular category. So the point I was trying to make here that we have to understand that there are going to be multiple solutions has to come together. Not one single solution is going to work over here. If we have to really cut down our total CO2 emission significantly. Renewable energy, let's look at how India has been doing in renewable energy. The data source is again the same data source. And this plot, if you see here, is from 1985 to 2022. And this talks about what has been the mix of our renewable and non-renewable energy in India. Okay, when we talk about renewable, it talks about electricity production from hydropower, solar, wind, biomass, waste, geothermal, waste, tidal, all kind of sources put together, which we club it under renewable. And you see how good we have done or how bad we have done. So the 85, we were roughly 25% renewable, 2022 are roughly 20%. So the point I was trying to make, it's not very easy to go from non-renewable to renewable. Okay, it's not only the data which is India specific, worldwide. We have been talking about renewable, including Europe, which has claimed that they have gone to renewable to a large extent. The overall improvement in from non-renewable to renewable has been only 4% worldwide. So in 1985, there were 25% renewable. Today we are 29%. With so much of discussion on renewable, so this is the problem of the energy or moving from non-renewable to renewable form of energy. It's going to be really steep. And since in India, we have not really moved that well from non-renewable to renewable, you would see that the total CO2 emission in India alone is roughly 3 billion tons of CO2 every year. This is 3 billion tons. Okay, it's not 3 billion kilograms. It's 3 billion tons of CO2 every year. Now, this is a huge number. It's a monster. We will have to see how we can basically contain this monster. You cannot really eliminate it completely. This is what we will talk about. So if I have to talk about 3 billion tons of CO2, so far I don't see in human history we have really technologically we have solved any such large problem. It's a very huge problem, and this is what I'm trying to basically point it out. It's a popular science lecture. I don't want to go too deep. Try to give a little bit of broad information. But this is the challenge which we are basically now tackling. How do we cut down our total CO2 emission so that every year 3 billion tons of CO2 is captured and put somewhere so that it does not go back to the atmosphere? This is the challenge. Okay. Now, one more data I'd like to give you. The way that CO2 emission is increasing in India is above world average. We are increasing roughly 5 to 5.5% every year. Okay. So if you don't do anything about it, 10 years time, you are talking about 6 billion tons of CO2 emission from India alone. So this is something which we have to be very careful about. The numbers are staggering, and the rate at which these numbers are going up is also staggering. For example, I will give you a data. Last year, the total coal consumption in India increased by 8.5%. So if coal is being consumed, where the CO2 is going to go, you know very well. It's not going anywhere other than the atmosphere. So please be aware that it's a challenge which is huge. And one has to always understand the challenge not moving for some reason. Okay. Now, talking about renewable, I'm going to touch about renewable a bit before I move on to CCUS. See, talking about renewable, many of you would have heard about solar panel installations, and in India, we have been talking about solar installation in big numbers now. Our target is very high. We have improved it, but we have not really reached the target. So our solar installation has improved significantly in last few years. The number is also latest, not really dated number. By 2022, we are 60 gigawatt over here. By now, it is roughly 100 gigawatt. Our target was, you know how much? 300 gigawatt. 500 gigawatt is the target by 2030. I don't know we are reaching there. I don't think we are reaching there. It's not, there are many challenges why we are not going to reach the target. I don't think it's only monetary, but there are other challenges also. I'm not going to discuss a lot on that, but what I was trying to tell you, let's say I have reached the target of 500 gigawatt. That's not going to be sufficient, but that's say this modest target we are going to reach. What we are going to do with this solar panel? See, solar panels produce the electricity only during the sunshine hours. So sunshine hours typically in India would be roughly 1/4 of the day, 6 hours roughly. Remaining 18 hours you are going to have no sunshine. So you are going to basically, what is proposed is, you are going to produce the electricity during these 6 hours, and you have to somehow store this electricity so that you can compensate for the remaining 18 hours of no sunshine. Okay. So if I am going to produce electricity for the first 6 hours of a particular day, if I have to keep consuming that energy for the remaining 18 hours, I need a storage media. Okay. And the storage media, mostly people talk about batteries, which I'm sure most of you would be aware of. There is a lot of sustainability aspect on batteries, storage of energy in batteries, which I'm not going to touch upon today at all. But the next best solution people talk about is hydrogen. Why hydrogen is very important over here, I'll talk about it in little detail. But the point is, if I have significantly large amount of surplus electricity during the 6 hours of time of the sunshine hours, I might be able to use this surplus electricity to split water. Split water means break water. Break water to do what? Break water to produce hydrogen and oxygen. Okay. So this hydrogen is considered as green hydrogen. Okay. If you are going to break water by using electricity from solar panel is considered to be the electricity which comes from solar panel is considered to be green electricity because no CO2 emission is associated with this electricity. So if you are using the electricity coming out from a solar panel and using this electricity, you are splitting the water to produce hydrogen, it becomes green hydrogen. Okay?
So you think only 6 hours, at least 8 hours or 10 hours is not
not every day. This is why it averaged out. So it averaged out over a year period. So there would be many days during the monsoon season when you will not see sunshine. So let's average it out. This is why it's roughly 1/4. Remaining 3/4 will have to somehow manage.
That's also depending upon the atmospheric moisture level.
Yes.
There are a lot of challenges.
So pretty much I'll tell you, see the question, it's not about 6 hours or 7 hours. It could be 7 hours also. That's not a big deal. The point here is that what we are going to do with for the remaining hour when there is no sunshine. So this is what is the point over here. That if I am going to store this electricity as hydrogen, and why hydrogen? Because if I have produced green hydrogen, I can either burn the hydrogen, okay, or I can basically use hydrogen to produce some other chemicals. It will be useful because these chemicals or these products which we are now going to produce with this hydrogen ultimately would anyway have to be produced. For example, if I am going to produce ammonia from this hydrogen, I anyway need ammonia for my urea and all other requirements. So if I'm using this hydrogen for urea production, then I'm not using any other fossil fuel for urea production. This is the point which I was trying to make. So hydrogen this is why very important. But let's look at how easy it is to do that. If I have to produce 1 kilogram of hydrogen by the current technology, and then this cannot improve a lot because thermodynamics plays a significant role over here. 55 kilowatt hour of electricity is needed. Minimum 55 kilowatt hour of electricity would be needed for you to produce 1 kilogram of hydrogen. Okay. So what is the cost of hydrogen today? Let's say you have 55 kilowatt of electricity from renewable source. Comes out to be roughly 3 rupees per unit you can get. So that comes out to be 180 roughly. Okay. 180 rupees per kg for kg. But then this hydrogen you cannot utilize right there. You'll have to transport it to the place where either you can burn it or you can convert it back into electricity using a fuel cell. So unfortunately, if you are going to transport 1 kilogram of hydrogen and store it, because you'll have to store it for many, many hours, you will consume around 10 to 15 kilowatt hour of electricity, depending upon how far you are transporting and how long you are storing. Okay, because hydrogen is a very small molecule. It does not stay at one location, at room temperature or any other temperature. It will, 1 second it will be here, the next second it is going to be over there. So you will have to basically compress it and store it. So the cost in compressing, cooling and all is significantly large. And this is why you are going to consume around 10 to 15 kilowatt hour of electricity for transportation and storage of this hydrogen which you have just produced. Okay, so that means that you are basically using roughly 65 to 70 kilowatt hour of electricity to produce 1 kilogram of hydrogen, because you have add this over here. And then from 1 kilogram of hydrogen, you can only produce 30 kilowatt hour of electricity. So from 70 kilowatt of electricity, which you have basically generating from a solar panel, you are only getting back 30 kilowatt hour of electricity. It basically means the solar panel which is producing for this 6 hours period of time is not supposed to produce for the remaining 18 hours, but it is supposed to produce for more than 24 hours, because efficiency has to be taken into account. Okay, so please be aware. Now you just imagine how many solar panels you are going to plant, put there on land. If you try to do these calculations, you will realize you are going to cover a lot of area from solar panels if you really want to move to renewable from fossil fuel to really solar panels. So this is something which people always have to keep in mind when they talk about, okay, we'll do all renewable and all. So I gave you an example how good we have done so far with renewable. Then I've also given an example of, based on whatever the thermodynamics tells you, is that what challenges you are going to face even if we are going to have solar panels all around. How efficiently you are going to do it is something which one has to always look at. So anyway, what I'm trying to say that hydrogen is a solution, batteries is a solution. I'm not saying that you should not do it. The point I'm trying to say is that you have to keep this in mind, that it's not going to be easy. Everyone has to understand the chemistry behind it. Then I come back to this particular slide. So what I was trying to say is renewable is not going to be very easy. So this very large green line which you see here is not going to be feasible for at least 2050 or 2060. Okay, maybe 2070, you never know. So if this range, what has to increase? This blue one has to increase. There is no other option, because we have to cut down this much of CO2. You can't do much. If one thing shrinks, other has to basically somehow increase its effectiveness, and we'll have to ensure that we are able to cut down to 700 billion tons of CO2 we are targeting now. This 2050 target is by the most of the country are targeting like 2050. So this is why people talk about 2050. In India, we have committed to be net zero by 2070. We have a little bit more breathing space if you talk about it. Now, many people will tell you, since this is a popular lecture, I have brought another additional slide in this particular talk today. See, many people will tell you, okay, fine, what we are going to do with the CO2? Can't we just plant more trees? That would be fine. All the CO2 which we are capturing, this 30 billion tons or 40 billion tons which we have to capture, where it will go ultimately? Has to go somewhere. No, otherwise how long will we keep capturing it? Or what we will do with that? Okay. So there are two options. Either you convert it into some chemicals, that I will talk. That's what the project, this particular talk is going to be on. But many people would say, let's try to plant more trees. It's the best solution. Let's go green. Now let's look at the math of this, how it looks like. Okay, so we need to capture 20 billion tons of CO2 every year for 2050, 22 degrees Celsius is what it is. Clearly say 700 billion tons. If you do a calculation, you will see roughly 20 billion tons of CO2 we have to capture every year. Okay, now can we sequester all these 20 billion tons of CO2 everywhere just planting more trees? Possible. Let's look at that, because everyone knows that CO2 will be consumed by the trees and then all those things. So look at the math. 1 hectare of forest will sequester roughly 10 tons of CO2. So if you are going to plant 1 hectare of forest, it captures only 10 tons of CO2. Okay. So all over in 2020 alone, 40 billion tons of CO2 got emitted, which is sequestered, and would require 4 billion hectares of land. And how much land do we have total? 15 billion. So you are going to plant trees on Earth in next 5 years, you will cover the entire Earth with plants, and that will not be able to capture all the CO2. Now do you see how big is the problem? This is why I was telling you that this is a monster. No doubt. See, I can feed you many times it happens. When you are a small kid, no, the kid would like to eat at a slow rate, the parents are not happy. So they want them to eat fast. So they will sit around him or her and then keep feeding him or her. Okay, this option you do not have. See, the rate at which CO2 can be sequestered under the sea is governed by the thermodynamics of nature. Okay, the rate at which CO2 is going to be consumed in the sea is say X. Okay, X kilogram per second per hour, whatever it is. Okay, now if you are producing CO2 at 100, what is it? Can you make the sea? So the question here is, if I am producing CO2 at the rate at which it cannot go into the sea at the same rate, then you have to worry about this. This is why the concentration of CO2 has gone up. See, the CO2 concentration traditionally, if you look into historically into the Earth's data, around 200 to 300 ppm is what it hovers around. Okay. Today we have already gone from that number to 422. And this is all numbers are, it's all a number game. And I, as a chemical engineer, on the game of kinetics. At what rate we can achieve something matters here. Rate at which you are emitting and rate at which you are capturing by natural source does not match. And this is why there is a problem. So did I answer your question? Okay. So moving on, so what I was trying to tell you that moving on, it's important for us to understand. Maybe the battery is on. No. Can you go to the next slide, please? Right now? Yeah. Yeah. Okay. Fine. So this brings me to the presentation which we wanted to do. I have taken a lot more time, but let me try to give you the background so that it's easier for you to understand. Now, what we are saying that we have to rely on carbon dioxide capture, utilization, and sequestration. Now, if we talk about CCUS, it's a three-step process to be very frank. First, you have to capture the CO2. Why capture? Because CO2 does not come as pure CO2. Okay? It comes as a mixture of CO2 with some other gases like nitrogen. Because what is the source of CO2? The source of CO2 is the carbon in the fossil fuel. Okay? Which we basically burn to produce the energy. So, if I'm going to burn carbon in this fossil fuel by oxygen, it is going to produce CO2, pure. But we don't burn it in oxygen, we burn it in air. Okay? The air is only 20% oxygen and 80% nitrogen. So that basically means that I'm using a dilute oxygen to burn this carbon. And because I'm using a dilute mixture, and because the carbon which we are talking about is coal, which has very high density, which we are trying to burn with a gas which is much lower density, we have to always supply excess of air to burn all the coal. Because it's not possible, no? There are hundreds of molecules in this small space of coal. But for every molecule of carbon to react with oxygen, I need 100 molecules of oxygen also, but oxygen is a gas. So oxygen, one molecule will be over here, one molecule will be somewhere else. So you have to bring it together. How do you bring it together? You have to pressurize it. Or if you are not able to pressurize it to that extent, then you have to supply more amount of air. So by doing all that, what we have basically achieved is that we have achieved the full combustion, because if we don't combust it completely, then it will be incomplete combustion and carbon monoxide will go. So we don't want that. So we have pulverized the coal. So we do all kind of effort to do what? To basically achieve 100% conversion of coal or carbon to carbon dioxide. But in the process, the gas which we get at the end of the day is highly dilute in CO2, because we have supplied too much of nitrogen, too much of oxygen to basically burn the entire fossil fuel. So the gas which you get from the point source is over here, is basically called, point source is called the industry. The cement industries and the steel industries I talked about. Why do they need energy? Because most of the processes happen at very high temperature. Okay, for steel to be basically produced, you need to go to 1000 degrees centigrade multiple times. Okay, for cement to be produced, you need to go to 1000 degrees plus temperature for multiple times. Where do you get all this energy from? You get all this energy from fossil fuel, and you'll have to burn the same fossil fuel in the same air we just talked about. So each of these processes produces significantly large amount of dilute CO2. What is the concentration of CO2 here? The concentration of CO2 here is roughly 10 to 15% carbon dioxide and remaining nitrogen for simplicity. Okay, there are other gases, but let's not try to complicate it further. It's already a complex problem. So for you to understand, let me talk about only two molecules. One is CO2 and other is nitrogen. Okay. Typically, the concentration of CO2 is roughly 10% to 15%, and the remaining is nitrogen gas. So the CO2 capture process is capturing this CO2. Okay. You are capturing this particular CO2. And this is explained better in this particular slide. Okay. So now you are seeing, can you go back? No, go back to the next slide. This one? Next. And one more. Yeah. So now what we are talking about, then we are talking about a gas which is a mixture of CO2 and nitrogen. And let's say this is a gas which is a mixture of CO2 and nitrogen. CO2 is this ball over here, and nitrogen is this ball over here. How I have differentiated the CO2 is I have put a Velcro tape on this CO2 molecule. Okay, why I have done all this? Because if I have to capture the CO2, I cannot just go and capture it. No, it's not easy for me to do. It's two different gases completely mixed with each other. What I need to do that? I will need a material which will be able to differentiate CO2 from the nitrogen. First, I need that material. Okay, and second, once this material has differentiated, then it should preferentially interact with CO2 to hold it, okay, and does not hold the other molecules around it. So this material has to be synthesized. You don't have any such material available in plenty, okay? So you have to synthesize this material. So what do we need? How this Velcro tape covered ball will be captured? I need a Velcro pad, no, which can capture the Velcro and the remaining will go. So I am talking about this pad, which is a Velcro pad. If these molecules goes around this pad, since this does not have a Velcro pad, will just go out and this molecule will get attached. What we are doing? We are manufacturing a molecule to capture the CO2 which we have emitted into the atmosphere, and since it's not pure, I need a material which is slightly exotic. Okay, exotic means this material should be able to recognize and should be able to interact with the CO2. Okay, why do I need this? Because there is lesser concentration of CO2, more concentration of nitrogen. At room temperature, nitrogen molecule have much more kinetic energy compared to CO2, which is much larger. This is why I have kept it as very good state. So the end point, what I'm trying to say here is that I would be able to basically use a material which will ultimately capture the CO2 and will release all the other gases. This is what we are trying to achieve. Now this we are trying to achieve from a point source. Now let me tell you the other option is that if we don't capture it over here from the point source, this entire gas will go to the atmosphere. And what will be the concentration there? 420. Okay. So now you imagine how big is the problem. In that case, you are going to have 2,500 molecules of nitrogen and 1 molecule of CO2. In this room, if you have 2,500 persons sitting there and you have to catch one guy from that, do you think it's going to be easy? It's going to be very difficult. So if I am not capturing this CO2 from point source, then where I have to capture it from? I'll have to capture it directly from there. This process is called direct air capture. If I am going to capture this CO2 directly from the air, it means I need an even exotic material which will be able to identify one CO2 molecule among 2,500 molecules of nitrogen and then capture it. So the material which I am going to need, this particular white pad over here, has to be really exotic. And let me tell you, a thumb rule is that if you are going to create an exotic material, you will do it with multiple steps. Okay? You cannot, in one pot synthesis, you cannot create an exotic material. You can create a simple material in one pot synthesis. Why I am talking about all this in depth, let me tell you. Any material which you are going to produce, humans produce any material, will produce CO2. Because we do not know to produce any material without creating CO2. So you will always need some energy for doing that, and the energy comes from the same fossil fuel. That's all we know. So if we are going to burn a fossil fuel, I'll produce some CO2. So today, since we are not capturing this CO2, we don't need this material. And please understand, this material, we are talking about 3 billion tons of CO2. How much material we'll have to create? This is what I'm trying to tell you. If I'm not capturing, I'm not creating that material. If I have to capture, I'm creating that material. And if I'm taking multiple steps to create that material, it means I am emitting CO2 multiple times into the atmosphere. This is why I tried to talk about the sustainability aspect of it. Okay, so the first question is the amount of CO2 which I am going to create. In creating this material, whether this material is good enough to capture at least that CO2. If it is not going to capture the CO2 which was created in the production of the material itself, then how it is going to create the CO2, capture the CO2 which comes out from the other processes. So this is something which people have to always focus on. This does not come into, typically people don't really talk about all this. So please be aware of that. Let me go back. So the question is that I have to capture CO2. Somehow I have a material which is very sustainable, very efficient, and I am being able to capture the CO2. What do you do next? You have so much of CO2 with you. So next point is that people talk about why don't you utilize this CO2? You will see in a lot of literature every day. If I do, that is my Google News suggests me those kind of news. Probably you may not suggest, but every day there are hundreds of papers and write-ups which come. Oh, this process can convert CO2 into this, into that, into diamonds. You will not believe even diamonds are produced from CO2 and considered to be a great development. Let me tell you what is the challenge there. See, if I am going to capture this CO2 and convert it into any chemical, what exactly is CO2? CO2 is carbon and oxygen. Okay. So if carbon and oxygen is the two elements in there, what kind of molecule which we basically would be using mostly? We will be using polymers, we will be using some other chemicals, we will be using fuel, all those things only, no? So what additional molecule I need in that? Hydrogen. Okay? Unless and until I mix hydrogen with CO2, I'm not going to say. Okay? Now the question is that, where this hydrogen will come from? If this hydrogen should come from splitting of water, so how much water I'll have to split? How much solar panel we will put so that I will get all the hydrogen, and it's not a small number. We talk about 3 billion tons of CO2 in India alone. So you can imagine how much hydrogen will be necessary for that. But the second question, which is more important, is here. See, the capture cost of CO2 from a point source is roughly 30 to 50 US dollar per ton. 30 to 50 US dollar per ton. Today I'll tell you the data which is India specific data is roughly $50 per ton. So if I'm going to capture 3 billion tons of CO2 at $50 per ton, what will be the cost? And who will pay for it? So if you do this calculation, you know today the electricity cost is roughly 3.5 rupees to 4.5 rupees per unit, depending upon what kind of coal you use. And if you are going to make this electricity green by capturing all the CO2 and somehow utilizing that particular captured CO2, the cost is going to be minimum double. So the question is that if I'm paying 10 rupees per unit of electricity, if tomorrow someone starts charging you 20 rupees, how many of us will be able to afford it? That problem is always there. It's not the challenge of technology. Technology exists, but the question is that whether it will be affordable or not. Okay, so the same question I'm going to ask you, if the CO2 cost is $50 per ton, and if the hydrogen cost, as you were trying to do this calculation, 180 rupees per kg, and if only 40% efficient you have, it basically means roughly 500 rupees per kg. So if I'm going to convert a 500 rupees per kg hydrogen and $50 per ton CO2, or 5 rupees per kg CO2 into a chemical, it will come out at 500 rupees per kg. So are you ready to pay, instead of 100 rupees per liter for your petrol, are you ready to pay 500 rupees per liter? So where you will use this chemical which you have produced? Utilization is possible. Science is there to utilize this CO2 and hydrogen. But what we will do with that? That's the bigger question. Do I have so much of money that I can do it? But there is a solution. The solution is that we'll have to gradually reach there. Because till few years back, we were paying 300 rupees for our LPG cylinder. Today, we are paying 1200 rupees, 4 times. No one is questioning that. So the point I'm trying to make is that everything is possible. We'll have to give enough time for it, and you'll have to have a plan for all this. So this is possible. The point I was trying to make is that sustainably producing electricity, capturing the CO2, sequestering it is possible, but you'll have to be aware of all this. Okay. I'm going to move on. I'm taking too much of time here, but the second question which I have in this other slide which I've added again because of popular lecture, not all scientists. People say, why do we capture CO2? Why don't we just use the CO2 as it is? What is the point in capturing CO2? Let it come at 10%, 15% concentration. I'll just use the CO2 to make a useful product out of it, and the nitrogen automatically will come out. Let me give you the data. If you are going to convert a CO2 into any chemical by thermochemical approach, thermochemical basically means that you are going to do a chemical reaction just increasing the temperature and using some catalyst. Okay. So by this process, if you are going to convert CO2, mixing with hydrogen and producing some ethanol and all, the most efficient process today is roughly 20 to 25%. Pure 100% CO2. Now, if you use 10% CO2 and 90% nitrogen mixture, you can imagine what will be the efficiency of the conversion, 2%, 3%. If you are going to use an electrochemical process, basically means that electrochemical, if you are going to convert CO2 into carbon or carbon monoxide and then mixing it with hydrogen to produce some chemical, the efficiency of the process is hardly 10 to 12%, maximum 15% is pure CO2. Now you do the calculation, what will be the case with 10% CO2 mixture. And if you are going to go for a photochemical approach, which is roughly 7% efficient, with 100% CO2. So this is the reason you need to capture CO2. You cannot do any process with this mixture of CO2 and nitrogen at a scale where you need to consume this amount of CO2. So this is the challenge, which is why we will have to basically talk about it. I want to leave some time for questions, even though the talk started a little late. I'll try to finish it off in the next 5 minutes so that you have whatever questions you have, I can take it further. So the question I posed you a question. In literature, if you talk about academia, they talk about a lot of exotic material for CO2 capture. Okay. So if you talk about this exotic material, the material can capture roughly 0.1 gram to 1 gram of CO2 per gram of this material. Okay. So if I have to capture 3 billion tons of CO2, I need 3 billion kilogram to 30 billion kilogram of this CO2. Okay, why? And because I can regenerate it by 100 to 1000 times. So if I have to capture 3 billion tons of CO2, I may need 3 billion kilogram of this material and regenerate it 100 to 1000 times, because I can only capture 0.1 to 1 gram of CO2 per gram of this material. Now, if I am going to, let me tell you a thumb rule. A thumb rule is that for steel, for example, 1 kg of steel, if you are producing 3 kilogram of carbon dioxide gets emitted, the best process. 1 kg of hydrogen which you produce today, black hydrogen, gray hydrogen, 20 kilogram of CO2 gets emitted for production of 1 kilogram of hydrogen. So let me tell you, if you are going to go and synthesize an exotic material like this, 1 kg of this particular material which you are going to produce, 10 kilogram of CO2 will minimum get produced. So it basically means that if I am not able to regenerate this material by 10 times at least, I am not capturing even the CO2 which was produced during the production of this particular material. And beyond that, I'll have to do 100 to 1000. So what has to be the focus? People who are in academia over here, the focus has to be on recyclability. Because if I'm not able to recycle this particular material for 1000 times, million times, I'm not going to talk about a sustainable process over here. So instead of focusing more on that, my material can capture a little bit extra CO2, what we have to focus on, how many times my material is able to basically regenerate, because maximum number of times you regenerate, more sustainable this process is going to be. Then if you talk, and there has been one such material, a friend of mine, Arvind Rajendra, in the University of Alberta, they talked about one such material in one paper very recently, and they have been talking about, they have been using this material for like more than 1000 times already, and it is performing. So the question I was always having of whether this is scalable or not, whether it can be recycled, or not. So he called me once and he told me that this is possible, and we are doing it. So this is why I've added this particular data over here in this particular talk. Now, academia, coming out of academia, let's go to industry. Industry, people say that we have been doing it from last 50 years. Our processes are available. We can always do it. The cost is not that much. Not that much means $50 per ton. So we can do it. Now let's look at the sustainability. So they do it. Most of the time, industry, basically, let's not blame them. It's all about every one of us does it. Our processes are optimized for cost. Okay? Any process we talk about, any product we talk about, we optimize the processing of this product for cost. How do we make this product at the minimum possible cost is what we focus so that my profitability goes up, the affordability goes up, all kind of things we talk about. We never so far look into how do I synthesize this material which is most sustainable. Because unfortunately, if you are going to optimize for sustainability, you cannot optimize for the cost. If you are going to make a product sustainable, it is going to cost more. So far our focus has been always optimizing the product cost, not the sustainability of the particular material. So we have to always focus on. So when they talk about these calculations, they talk about, they say that we have a molecule called monoethanol amine or a derivative of this particular amine, which will be able to capture the CO2 so that when I burn coal in air, I will be able to produce the energy and all the CO2 will basically be captured by this particular amine. And nitrogen I can release it to the atmosphere. But we have to go one step back. This is the cost they're talking about, this $50 per ton, capturing and regenerating this particular material. If you talk about going to one step back, you see this molecule does not come from thin air. You have to synthesize this molecule. And how do you synthesize this molecule? It gets synthesized by reacting ammonia with ethylene oxide. Okay. Now, ammonia today is produced from fossil fuels. Ammonia production process is very high temperature and very high pressure. Haber-Bosch process actually people talk about. This is the same process. So there is significant CO2 emission in production of ammonia itself. And then ethylene oxide today you will not believe there is no other source of ethylene oxide from the same fossil fuel which you are not trying to utilize. Okay, there is no other source of ethylene oxide. You will have to, if you want ethylene oxide, it will come from the fossil fuel which comes from under the earth. The only other source of ethylene oxide is bio-based product. Now, I have already given you an option of planting tree on the earth, and in 5 years you will cover the entire earth. Probably you can use that biomass over here. But the point I'm trying to make is that this is not going to be that easy. When you try to do all this, everything has to be talked about. Now, I'll give you a few more details in this particular presentation. This is the largest direct air capture plant which exists on the earth, which is called Mammoth and also called Orca. Okay, this is in Iceland. This is from this organization called Flying Worm. Okay, and this captures 4,000 tons of CO2 every year, which is what 1 second of CO2. This is a huge plant. You will not be able to see the footprint. You can compare the footprint of these trees with this particular plant over here. Huge footprint, and it is 1 second worth of CO2 emission which we do. And I will give you another image over here. This is from China. Only 10% of the total plant is shown in this particular figure over here. It is basically capturing CO2 from a point source, where the concentration of CO2 is higher. 160,000 tons of CO2 per year is converted into fuel. Okay, and this is worth 2 minutes of overall CO2 emission of the world. Okay, this plant is huge. So what we talk about in our group is that let's not produce a new material for capturing CO2. Let's use an existing material which is there already on a. If I can use the CO2 which is there in plenty, I might not need to create this material. If I'm not creating this material, at least I'm not emitting that CO2 which will come for the creation of this particular material. And if I can optimize my process better, then overall the sustainability percent in this particular process will be slightly better. I'm not saying that you can do it without any cost, without any other, this is the god of the process, nothing like that. Just that we all work with different processes and we try to go for. So in this particular case, you have a gas mixture going in, and by the time it comes out, there is nothing else other than water in this particular process, which has been basically demonstrated. And since it's not technical talk, I'll just skip it. This is the demonstration unit which we have in IIT Madras. If you happen to be around, drop me an email, I'll be able to show it to you. We also do a lot of work on whatever we talked about. So we basically design right molecules which can capture CO2, then we test it in the lab, and then we basically go to the pilot scale to test it out. What would be the energy consumption? How sustainable is this process? So all this we basically do. Now this is the unit which we have recently delivered to L&T. This is the exact unit which is going to be implemented. This is directly capturing CO2 from air. Okay. If you look into this particular image over here, this is the test room where the CO2 is being, because you have to do it, a pilot testing has to be done. So you have to supply CO2 and then study how the CO2 rate goes down by this particular process. So if you see here, there is a unit over here which basically sucks the CO2 from that room and then basically puts it at the bottom of the reactor, and this material over here basically captures the CO2, and by the time it comes out, there is free of CO2. Okay, so this unit has been already delivered to L&T. They are implementing hundreds of such units all around, but let me be very frank with you. None of these processes will be able to capture more than 1 second worth of process situation. So this is something which will always have to basically keep in mind. And the next part is that if I am going to capture all this CO2, what I am going to do with that? So there is a very nice way of basically storing this CO2 or sequestering this CO2 under the seabed. This is the seabed, and we talk about sequestering this CO2 below the seabed, 100 meters to 1000 meters below the seabed. Why below the seabed? Because you cannot put it above the seabed. It's in the water column. If you are putting CO2, it will acidify the water and all. And he was talking about the natural process. If I try to enhance the process artificially, then I will acidify the ocean. It's not going to be very amiable for all the flora and fauna in the ocean. So no one would allow you to do that. But what you can always do is that you can put that CO2 100 meters to 1000 meters below the seabed, so that this CO2 does not come out and get converted into this kind of solid hydrate. So we have basically a demonstration unit for that as well, where we have demonstrated it. That's all for today. I don't want to take too much of time. So please ask questions. Don't be shy. I'm not all knowledgeable, but whatever little I know, I'll be able to explain. It's not accountable. What we talked about is anthropogenic release of CO2. So humans are very small compared to nature. So if you want to emit billions of tons of CO2, we anyway can't control it. What we talk about is what we can control, what we have contributed to. So this is what we talk about. So 3 billion tons of CO2 which India emits are because of our activities, not because of the nature. So how do you we are not bothered about nature. We assume whatever nature will do, anyway we can't control. And whatever nature does, it basically takes care of itself. Whatever we are basically doing, the additional which we are emitting is what we can capture. No doubt, I agree with you on that aspect. But whatever we are capturing is what we are emitting. That's all we are talking about. So we are emitting 41 billion tons of CO2 around the world today. It's anthropogenic release of CO2. So we are only talking about capturing that. And let me be very frank with you, this is the CO2 which is going to the atmosphere and increasing the concentration of CO2 in the atmosphere, not the natural one. Natural one has been there for millions of years. Okay, there could be a cycle more and less, but overall, on average, they have been doing it, and 200 to 300 billion used to be the case. It's only when human arrived, they started exploiting it, and this is when the CO2 emission has gone up. Can you comment about the CO2 and so this is a very different topic, but EV vehicle is of today, where your electricity comes from. The same fossil fuel, okay? So if you are using that electricity, and if you don't convert that energy into electricity and then charge your batteries, and the batteries has to be produced by 10 different minerals are required in batteries, 10 different minerals will come from 10 different mines. What is the concentration of the minerals in the mine? 1%, 1.5%, 2%. So you are processing that entire material to get this 1% of the material 10 times over. The question is that if I am going to use the same fossil fuel to do all this nonsense, why don't we just run the ICE vehicle? So overall, the CO2 emission is going to be much higher. But yeah, tomorrow, if I have green electricity, then it will work better. But then again, I am not talking about the LC of batteries today. That is a topic which I can talk about on some other day. But you will have to do a life cycle analysis of batteries. What is the CO2 footprint of batteries coming on this table today? And then how long these batteries will work? And then how many 5 years down the line or 7 years down the line, if I am discarding it, how I am going to handle it? And what will be the CO2 footprint at that time? All this has to be calculated.
So what's your opinion is, your son was opinion for that? Just in active in the context, method to control. So what in your opinion is the production of carbon dioxide the best way to go and having the best way to go? Nuclear energy the best way? What would you mean? There's so much happening around that.
That's a very good question, and this is why I pointed it out that there is no one good solution over here. See, even though the CCUS looks pretty difficult to do, you will have to, in short term to medium term, rely on CCUS. There is no other way out. Okay, because the amount of CO2 which is being emitted today is so much that if we keep talking about it, it will keep going up, and then the concentration in the atmosphere will be so high that it will take some 200, 300 years for us to bring it down. Because if we keep capturing the CO2 directly from the air, it will be very costly affair, and all kind of challenges will be there. So the second point which you talked about nuclear, certainly this is one approach where nuclear, if you know how to basically handle it properly, will be a better solution compared to any other fossil fuels and renewable put together. But this is the policy decision. This I cannot talk a lot about. But nuclear has its own challenges. Most of the challenges have been sorted out. There are few challenges which I'm pretty sure people will be able to sort it out. This looks like a very solution. Nuclear is being controlled by just few countries. A lot of things have to be done. A lot of red tapeism is there. All those challenges, I don't know how people will handle it, but this is going to be a challenge. And by the way, if you are going to put a large nuclear plant today, it typically takes roughly 15 to 22 years before it can start producing electricity. That is another thing which one has to look at. The gestation period is pretty tight, very long there, and one has to worry about that. So the policies have to be taken fully if anyone has to do something. I know I have not answered your question directly, but yeah, this is a challenge which we will have to take one step at a time.
Just one other thing, there is a group that says global warming is the next, and obviously private at the time is looking at the data, obviously what do you say to that? It's a big group that says there is no global warming.
People used to be believing this, not anymore. The number of people who used to believe that it's a myth has shrunk significantly after seeing what is happening in last 5-10 years. But again, I think this question was also pretty similar, that see, you cannot really control nature. Whatever we are trying to control is whatever we are doing. So if we are just trying to do things, nothing more than that. See, I'll give you an example. For such questions, I give an example of those days. We talk about a lot of civilizations in India and all, Mohenjo-daro and all. Those days we were not emitting so much of CO2, and still those civilizations got lost. Why they got lost? I don't want to talk about that. But the reason is very simple, that you can only control up to a certain extent. So if nature decides to do something which we can't really control, we'll have to accept that. But whatever 30 billion tons, 40 billion tons which we are emitting, we'll have to ensure that we at least capture that.
We're talking about global warming, 2% increase before and after industrialization, but it's only linked to CO2 or it's a methane emission we consider. It's still a different topic, but
no, it's not a different topic, it's the same topic. CO2, CH4, all these gases are being emitted today, and one has to capture it. One has to capture it. Now, which is contributing more, obviously depends which country we are talking about. In India, we have to worry more about CO2 right now. And it's the pH thing is a little sensitive. I don't want to go into, maybe we can one-to-one have a few discussions. But if it's typically talk on CH4, I'll talk about CH4. Otherwise, in this talk, I'm not going to mix CH4.
Because of the capital coming,
So this is what I'm trying to say, that these are very sensitive topics. Let's not talk about that, and it will divert the attention of the public over there. I'm aware of the question. Just that I choose not to answer it right now.
So, thank you for this lecture. It's very, very good. So, sir, actually, I want to ask one very question that in this question, this much discussion for the country of the world, international arena must have grown and also took many agreements, many organizations, moderate protocols, Jali agreements in this concept, free development mechanism, and joint cooperation mechanism. How is the impact of it to control these PhDs and PhDs? Is it positively or negatively impacting the world?
Every intervention you talked about is with the intention of positively impacting it, not negatively impacting it. But I don't want to go again in politics, but I'll give you a small number here. You see, I told you about this CO2 capture cost. Now, I also talked about who is going to pay for it. It's not that the technology is not there or we need to really identify something which is out of the box there, and it's not going to change a lot. So the first question comes to our mind is that how do we ensure that it is implemented? See, we are talking about it from last 10 years, at least in India, lot longer in other part of the world. But today, not a single plant, commercial plant, captures all of its CO2 and stores it or sequesters it. Okay, so this is the data. Why it is so? The data very clearly, this is what I pointed it out, that we have a habit of connecting everything to the cost. Okay, I mean, you and me including are culprit of it. We always say we will only pay so much, or why there is an increase of 50 paise. If we keep looking at that, it's not going to be sustainable. Because I'm pleased aware that we are living on borrowed money from our future generations. The cost which we are paying for all our natural resources are way too below what it actually costs. Okay, so how we are doing it? We are just doing it because we are borrowing that money from our future generations. And this is how we are able to sustain it. I don't know how long we are going to do that. We have to come to our senses. That's all. This is the only answer I can give you to this point of time. But the cost which we pay today for our petrol, natural gas, sugar, rice, wheat is much lower than what it should actually cost. Much lower. So please, next time onward, don't start thinking about when there will be increasing cost because of sustainability. You will have to pay for it, no doubt about it. Cannot come at the same cost as what we are being used to do. So I'm sure many of you know rice, sugar and all. You will not believe how much water gets consumed. 1 kg for a production of 1 kg of sugar and rice consumes 3,500, 4,000 liters of water. Do you really believe that 30 rupees is the cost of 3,000, 5,000 liters of water? We are paying way too low than what actually is cost. We have got used to it. Why? Because we know that we will get away with that. But it has been the case so far. I don't think we will get away with that any longer.
Like you said, the mechanism for remote mechanism, if you control the own emission of CO2 and other safety gases. And regarding to the anthropogenic emissions, what about the other elements which also cause carbon warming? Of course, it is outside the problem is of the lecture.
Nothing is outside, everything is inside the problem. I'll tell you one thing. I've already answered that question when he was asking something very similar. See, any natural process you talk about, it's a problem of rate at which you can do it. For example, I'll tell you when iron rusts, it produces hydrogen. So can we say that we will start rusting all the iron and that will be sufficient for our hydrogen needs? Rusting is a very slow process. How much hydrogen will produce from that? Okay, so the question here is that when we have to use so much of energy today, and when that much energy requirement is increasing the weight of CO2, we talked about that number just now. So that is the bigger question. We have to understand how do we control it. See, the other question is also the economy is decided based on GDP and all those things. So if you are going to consume more, how do you say that I will produce less CO2? So if I have a target of reaching 10% or 12% or whatever that number is, can we tomorrow start saying that I will reach 10% GDP with 0% CO2 emission rate? Not possible. You will have to accept it and then you'll have to say, okay, fine. Either you have to keep that or this is the target. This is what I was trying to tell you that as an industry, we have to always worry about what are we going to optimize it for, the cost or the sustainability. I think it's the time that we should start optimizing every process of the sustainability rather than the cost. I hope I answered your question.
Thank you, questions. One is that you mentioned about storing the renewable energy in hydrogen farms. So it is a viable option, and so that is not that much viable.
No, I'm not ever said that this is not a viable option. Batteries is still a viable option. That's the technology which we already have. Otherwise, if you start discarding all the technology, then what we will use? There is no other possibility, no? Right now, there are many other things people talk about storing energy. A lot of things are people talking about. Pumping water from bottom to the height of the mountain, that is also a storage option. So many things are there. It's not only that hydrogen and the batteries are the only option. A lot of things people talk about. I'm sure there are a lot of literature on that. So I don't get your question. What exactly you are trying to ask?
Manufacturing battery, carbon footprint of creating batteries.
See, I don't want to be sounding negative, but I am just trying to warn you because since the topic was on CO2 footprint, see, we are trying to reach net CO2 neutrality, no? So if you are going to achieve net CO2 neutrality without talking about CO2 footprint of the process, not going to happen. So this is why I talked about the CO2 footprint. Everything we do today, I mean, I always give this also as an example, that since when we were kids, I remember very well, either due to less money or whatever, we had few closed spaces, 2 pairs, 3 pairs. We used to keep it inside a box. We will go to a marriage and we'll use it once in a year or two and all. Today we have to squeeze in my own cupboard. What can you tell? Now every molecule which was used to produce that cloth had emitted CO2. So I am equally responsible for this CO2. We have multiple pairs of clothes, multiple pairs of shoes, even my glasses I try to use every day one other glass. So this is the greed which we have. We have to cut down our greed. We cannot do much about it. Because of the greed, all this CO2 has come to the atmosphere. So I don't know what can I say. I mean, yeah, we'll have to change our life. But this is all being done in the name of GDP. Let me be very frank with you. If I don't consume this, our GDP is not increasing. So you have to look into that aspect also.
I think one of the and the second question is, capture carbon dioxide and industry 0.44. So is the industry in India ready to implement those capturing methods, at least government agencies?
Everywhere it is ready, not only government, private, everyone can do it. Are you ready to pay 20 rupees per unit? That's the question. This is why I already pointed it out. See, I'll tell you, it's not about you though. Today, 400 million people in India does not pay for their electricity, either because they can't afford it, or we believe that they don't afford it, or they can't afford it. This is why we are giving them for free. So, at 10 rupees, if they are not able to afford it, what do you think what would happen at 20 rupees? And if so many people will not be able to afford electricity at that rate, then again this question of GDP comes into the picture. How will we go? So see, these are all very chicken and egg problem kind of thing, no? Which comes first, which we'll have to handle first. So this is why I always said that it has to be slowly eased out. People have to basically accept certain things and slowly move in the right direction.
It's just a political question or political.
I don't want to go there though.
One stage, the scientists like this, we start to like to avoid it. But outside we have to take the political diversity also.
I think rather than political, I think it's more about policy. We have to have the policy to drive certain things. Means BS1 to BS6 we have reached in regular emissions, not without policy. Okay, there used to be significantly large amount of emissions of carbon soot, SOx, NOx, and all kind of things coming out from our tailpipe of vehicles. Today we are talking about BS6, where we have completely got rid of pretty much the diesel vehicles. Even the petrol vehicles in BS6 are not polluting as much. So we have achieved many of these things. We have been able to do it. You know why? Because of the scale. The rate at which emissions comes out, the poison emission is much smaller. We are talking about ppm level over there. But the CO2, which is the product, the main product of our combustion reaction, we have not handled this kind of problem. Tons and tons, we don't know how. That's the reason. Also, we know how to handle it. The cost is basically brings all the time. Yes, you have some questions. Sorry.
Sir, our industry ready to capture and how the infrastructure is the most efficient.
Infrastructure for sequestration requires huge amount of pipelines and all is not ready yet. Not ready yet.
Is it required to get into the sea, or we can do it on summer coal mining?
Coal mines is certainly possible. Empty oil and gas fields are certainly possible. I think the first low hanging fruits are there. We'll have to basically start from there. And then as we ramp up, when all these resources in the terms of storage resources fill, we'll have to go for those cases where we will have to probably spend a little bit more infrastructure to achieve our goal by 2070. If we have to achieve it, we'll have to do it. There's no other way out.
So I'm just curious to know what are the kinds of materials we can use that can selectively capture CO2. Like we said, instead of synthesizing new materials, we can try for alternatives which are available in the industry. What kind of materials can do that?
I'll tell you the process which we developed in our lab is water-based. It's basically a slow process. And only works when your concentration of CO2 is around 25% of CO2. So if I have a CO2 concentration which is below 25% CO2, that process does not work. See, the problem with nature is that the material which is available in nature is very not exotic material as of now. So the rate at which it can capture, is much smaller. So I don't know, I have not answered your question, but this is what I am trying to tell you, that these are challenges still there, which we will have to. There are other materials, clay, sand, and all those things which you can certainly use. But the rate of CO2 capture there is going to be much smaller. We have to compromise something if you are going to. Yeah. This is why I say it's important for us to do a very proper life cycle analysis of the processes and try to look into what works better compared to. This is what we are trying to do in our lab. We try to develop some of these processes through calculations and through experimentation at large scale to figure out which process will be better compared to. This is a very pertinent question. I agree with you on this. I'm not saying that I'm saying that when you synthesize, look for more recyclability rather than more storage capacity. This is the point. This is the take-home message from that slide. I mean, it might look a little negative. I will just to give the concentration difference has to be more. No, this is why I gave a little bit more negativity, but don't worry about that. Possibility is still exists, but we'll have to be aware of it. That's what I wanted to say.
Two questions.
The first one, you given had only two questions. I wanted 3 questions.
The first one is regarding utilization and sequestration. So after carbon capture, we have these two choices between utilization and storage, and both have their own advantages and disadvantages. Like utilization
economic incentive,
but sequestration, what I read was it can lock CO2 for a very long time. So at what point should an industry or government or anyone choose, like, At this present condition, maybe utilization is more better for me, or I should go for sequestration. So, what is the thumb rule that you feel is right for me?
The thumb rule is that you do whatever is possible. Okay, if you don't do anything, no, then whatever comes your way, you will do that. That's the thumb rule.
To go little deeper,
See, utilization, even if you are going to
a process which is very
efficient and will be able to utilize CO2 at the cost at which this product is going to be available. You can at max utilize only 15% of the CO2 which we are emitting. Remaining 85% of CO2 which you emit, you cannot utilize and sell it because there is no demand for that product. There is no going to be a such product which will have so much of demand that all your CO2 will be consumed in the process. Okay, maybe you can start converting that into a food. That is also a possibility at some point of time. But the point I'm trying to make here is that in the short term or the medium term or the whatever long term we talk about 2070, sequestration has to be part of the game. Without this, you cannot basically achieve that net neutrality of CO2 by 2070.
So, my second question, since we talked about sustainability of the process itself for materials itself, now we have
hype is on solar.
but they have their own controversies, right? A long back, solar panels are produced by a certain country, and they said that the lifetime also 30 years. The cost is high, but it can last for 30 years. But now the most popular ones are produced by some other country that comes for 10 years. And the biggest issue that we talk about in solar panels, how do we dispose those metals? And for battery, we have the problems of cobalt. And in many articles, the criticality of these metals that we use in various processes that is being considered. So, while we are focusing more on CO2 emissions and controlling all that, are we forgetting the other aspects of sustainability? So,
I found him to the smartest in that group though. Where are you studying, by the way?
Chemical engineering.
Chemical engineering. See, the chemical engineers are smart. Very pertinent question. I have no really thought answer for you on this, and I'm sure you also know about it. So you are just asking because you wanted to be here and asking this question. The reality is that these are the questions which we are trying to answer. And I'm sure we will be able to answer partly, and we will have to wait for some more time to get the right answer. But this is the reality. You are right, and you have basically summed it up quite well.
This particular custom we were discussing about more than 10 minutes. In fact, now we are discussing more about this environmental legislation in India. But almost 10 years before, it's a global discussion. In fact, European countries and US one thing. Denmark has started capturing the carbon dioxide and doing that has been completely supported by the government, and of course, a lot of startups also paying. But how does India stand now? What is the and one more thing is, we are discussing this particular point only within us. That means institutes and corporates. That's it. I don't think this is reached to the common people, and they don't know what is happening.
This is what I was thinking. I'm talking to the common people.
Yeah. So
this is not industry. I'll tell you, I doubt that common people does not know about it. Maybe they are not 100% aware of the challenges they are going to face, but everyone knows about it. And this is one really good thing which has happened. I'm telling you, even that small girl sitting there, I'm pretty sure she knows about it. And this is why she's come here, otherwise she would not have come.
Everyone knew global warming.
Yeah.
They know what is global warming. But intensified, we go inside this much of awareness. I'm saying that it has not gone to the different parts of India. I mean to say like a pair of people is aware of it. If you go to the villages, they don't even know it. So that kind of awareness and that kind of thing, and in India especially, where we stand and when compared to other countries.
I think we are quite aware. If you talk about awareness, we are quite aware. I think every country has their own challenge. When you are a small country and you don't have that much restrictions of the monetary and all, that's why it comes easily. when you have a large country where there is huge amount of disparity among people, and you have to always worry about the affordability and all. Solutions which you have to propose has to be very simple, as well as solution is basically cost enough so that everyone can afford it. I think the affordability is a big challenge most of the time. You have also talked about it, that people talk about it, and I'm sure what you mean is that we have been talking about it and doing nothing. I think that doing nothing comes mainly because of the affordability problem.
But I'm from the corporate, I'm from the administration. We used to give awareness to the employees that why can't we go with the carpooling? Initially 10 days they all interested to go with them. 11th day, everyone comes with their own car.
I agree. But this is not the problem of not being aware. No, you have been made them aware of the problem.
No, I'm saying that. I'm saying that corporates are aware of it. When we talk about the end of
you everyone is aware of.
yeah, thank you.
We still do it because we don't want to change our behavior. Yeah, it's a habit which has to change. We don't want to change. And it comes, you know why? Because we have become a bit more, I would say, quote unquote, richer in that sense. We say, why, if I can afford it, why do not I do it? That's the point, actually. Nothing more than that. I think she has another question there. Yeah.
Good evening, bro.
Good evening.
How industrious in your project where you said that you are giving a machine to NASI, where it is carbon capture? And as I know, and like in this country, professors are into specific area of these are very less, countable in hand number. And like, as we grow forward this country and the world also sees this economic, environmental economic challenge. I think we'll be in a war food thing for like maybe after 1 decade, maybe people will be regarding elections on this issue and spending this issue, how to control. And carbon capture, for technically some of the solutions we have. And as you said, you given the language that's for air, right? Yeah, so I think if you want, like, if you look into the future into such war fooding and to be standing in what we doing in international forums as a country to serve, we can do something for the CSR initiative, compulsory CSR for which about the policy. And how industrial is like professors like you are, people who are manufacturing machines or technology associated with carbon capture, either at source or at atmospheric level. What is this scenario around the country now? How many institutions are funded or because it's all in-house funded. This country only funds this, and especially only funding is coming from the government side. So no other country is bothering. They are not going to hardly take care of their country. So other than two Nordic countries, no one has really taken an interest in doing it. But we are on a war food. Maybe 2050, 2060, we have to go there, and maybe that will start by the end of this decade. So I really want to know how industrious your projects are and how industrious you are hoping to make it. Because unless it is why industrial project, it can't see what I'm thinking. So
okay, very good question. But before I answer it, let me tell you, any academic institution are an academic institution. Okay, what is our role? Our role is to basically do the holistic research and give solutions to industry. So when you expect us to become industry, then it will become a challenge. Okay, what we can only do is that we can help industries like LNT and others to basically reach there.
Yeah, that is what I think they are in the outreach program through the academic institutions. Because in a country like us, people, as you said, LNT, the people can afford that price, like LNT. I think now it costs more than 500 companies. Like we talk about 500,000 important companies in India now. So that runs to 500,000.
Are you sure industries will do it without worrying about the
CSR components, starting with the environmental air capture from their plants, as little as possible. We not fix as little as possible. They can start investing in.
No, I'm sure everyone agrees with you. I also agree with you. The only concern I am having is that.
No, as a country, we are really thankful, need to bridge that gap between the academia and industry. It has not taken place as a policy also much, other than
I think my part of the blame, that academia should reach out to industry.
No, I think now it is there. You have to time that maybe even Americans, later on, I think you are that goal. Because I need few professors into such enterprising areas, because this has to be enterprise. In future, this is an industry. You have to go
about this cosmetic, I think we are not the nice here, to be very frank. I'll tell you very clearly. See, the one, yeah, but what I'm trying to tell you is that everyone will have to come together. I wanted to point this out that we are trying to reach out to industry and industries are also trying to reach out to us. I'll answer the question, don't worry, I'm not trying to go anywhere. See, Energy Consortium is one such organization in IIT Madras which we have now. This Energy Consortium, one of the biggest targets for this Energy Consortium is to decarbonization. Okay, right now we are working with 11 different partners which are industry, MNCs, Indian and all, and there are roughly around 56 faculties in IIT who is basically part of this consortium. We have kind of delivered or delivering close to 23 such projects right now as we speak. So, but I'll tell you, this more has to be done, you're right. And we are aware of this.
I think the management school, something should come in this.
No doubt. I agree with the
Collaboration, I think we should move towards like, do a kind of like overall investment, unless then it is not possible.
I know. I think one of the biggest challenges in India has been that we don't collaborate.
Because there is no university space, there is no idea of collaboration.
It's not the institutional problem, it's personal problem too. We don't talk to each other that often. So we need to talk more.
This is a common line question. I know, substance, the functioning, is generally carbon dioxide, which is the do these companies support research and development in carbon dioxide storage and capture?
I will tell you, in industry, there is no dearth of the CSR funds which we talked about. And also, there are no dearth of industry who actually want to invest in this kind of projects and are actually trying to bring out a positive change in their future. But then again, they are typically driven by the boardroom discussion. Okay, and typically still it's more profit oriented than anything else. And they are trying to, so far they talk about will monetize this problem. Only I have a problem on this particular statement, monetize this problem. You cannot monetize every problem. Okay, there are certain problems which he rightly pointed out has to be solved from sustainability and from social angle. If you try to monetize everything, and this is what I know, and this is why when we talked about bringing management and all, I think we have to bring all those people and tell that every problem you can't think of monetizing. Yeah, it's good that you will try to see that if there is profitability when you're able to do it. But then till that comes, it might be too late for you to do. So it's important for us to understand that there are some problems where we cannot always keep talking about monetization. We have to solve it as soon as possible. And this is one such problem. This is why at the start of the talk I talked about this monster. And we will have to basically somehow contain it and forget about monetization of this problem at least. Let's get all the money from selling the drinks than creating that CO2. Super.
We are almost 14 days going to be using our water tank probably. It's going to be done by our Joint Secretary, Verma. Basically, so Science Forum is working on creating awareness. Science. So we are popularizing science. We want to focus more on the science behind the carbon. Again, there is multiple angles. We have social thing, political, everything is connected with this issue. If we start bringing in all those things, no, we can deal in Science Forum. Again, we are in the election time, we can't go beyond certain things and we can't discuss those political issues here. So better to restrict ourselves with the science related to the carbon fixation. The professor has bring in all the issues related to why we go for a carbon fixation. We have got a lot of options, and each option, what are all the limitations we have. And finally, he concludes that we have to capture here and there. Each component should be utilized and to arrest the monster. We have a monster before us. The monster has to be arrested somehow. And if you try in one angle, and it is not theoretically possible. It is theoretically possible in many cases, that we have to bring everything together one by one. That's why he brought before the table all the possibilities in science. And we have to, it is the society to decide how we are to see this. He also indicated that the way the lifestyle and our social disparity, so many things are there. Everything should be considered and find out a solution for this. And we are opening a floodgate for a discussion on this. We are science forum and we limit our discussion is limited to the aspect of science related to this. Please bear with us if you get some disappointment. I would like to apologize because we can't go beyond the minute. That is how we are restricting it. Sorry for that. With this, let me thank Dr. Rajnish. Yes, wonderfully, he got a wonderful lecture. And the day one I started him now, it's amazing. It's like to share everything what is the experience. How many people have? Because plenty of knowledge, willing to share with the common man. It's something amazing. And I invite Dr. Kumar to give the order.
Moving on. So, before going to my formal responsibility, with your permission, can I ask one question, please? Yeah. That is, before coming to this lecture, I was in person that, we Indians have a very low carbon footprint. So, as a country as a whole, compared to other what is our responsibility of reducing our carbon footprint? I mean, we are only, higher responsibility or our responsibility compared to when?
See, per capita we are quite low. But when we talk about overall, it's quite high. And I think, I don't believe this West comparison and all, because see what has happened, China and India right now is manufacturing for the entire world. So it's not the CO2 which you are emitting only for your own population, you are also emitting for the other people. So all the service sector which we have in India and the CO2 which is being emitted from the service sector, who should be accounting that CO2? The US countries or the European countries should not account for that CO2? See, all the European countries which they are producing, the entire product they consume are coming from China and other countries. So who is responsible for the CO2? The people who are consuming or the people who are producing? So one has to always look into all this, because nowadays in this global world, how do you count which CO2 is going where or coming from which person?
It's a global effort. Yeah, it's a global issue.
It's a global issue and we are quite large in terms of total number of CO2 coming out. 11 billion tons is China roughly, and we are 3 billion tons. Not too far off from them.
So it's another dimension of the monster.
It's certainly a monster.
So thank you all for coming for this lecture. Normally, the lecture will be longer and the questions will be less. Now, in fact, today the questions were, you are beautifully answered those questions, touching upon various within the limitations you touched upon human behavior to the technological aspect of the monster. So thank you, Vidman sir, for your spending time. And I thank all my colleagues at the Tamil Nadu Science Forum and the authorities, the library authorities, they provide the space. And last but not the least, the partners. Thank you all.
One announcement, please leave your